Good morning, everyone. I want to start out by saying that everything I talk about this morning, I did as a high school teacher. I taught high school for 7 years, 1 year in Illinois, um, and then 6 years in Wisconsin. And the nature of science is something that can and should be done seamlessly with teaching science. So this is not something you do in addition to teaching science. It's something that is part and parcel of teaching science. So I want to talk about what we mean by nature of science. Um, it addresses more than what I'll put up here, but it includes issues like what science is. It seems like it's a simple question, but it's really more difficult when you get down to what is science, what isn't science, how science works, epistemological foundations of science. And what we mean by that is, how do we know what we know? We tell kids a lot of things, but how do we know those things? Ontological claims in science. Science says that there are atoms. Are those atoms real? We now think they are. But if you go back in the history of science, even Einstein, for much of his career, thought that atoms were heuristic devices, that they weren't real. And so science makes ontological claims about the natural world, what really is there, and that's part of the nature of science. How scientists work. For example, we oftentimes wrongly teach kids that scientists should be totally objective. Well, to what extent can and should scientists be objective? Science is oftentimes portrayed as a lone endeavor, not as a collaborative endeavor. So how scientists work is something that the nature of science addresses, and then how society influences and reacts to scientific endeavors. Again, I don't want to imply that this is all of the nature of science, but it gives you an idea of what we mean by the nature of science. We know from extensive research that misunderstandings regarding the nature of science are widespread. You can see that in everyday media and how people respond to science. We know these misconceptions contribute to poor personal and public policy decisions, negative attitudes towards science, unnecessary conflict between science and religion, and difficulties in teaching and learning science. Question arises, how do these nature of science misconceptions develop? Well, first we have the media portrayals of science. The way science is spoken of in the media sends mistaken notions. Let me give you an example. Just recently I read an article about why is it taking so long to get a COVID-19 vaccine? And I'm thinking to myself, so long? They've only been at this a few months. The way the media oftentimes speaks about science sends the view that science ideas are developed rather readily and that we reach well-established knowledge quickly, when in fact it can take months, years, decades to establish scientific knowledge. We know science textbooks distort the nature of science. The way they convey the knowledge, my favorite example from a high school text I used when I taught high school, in 1953, Watson Crick discovered DNA. Really, just like that. Again, it sanitizes the process and it portrays science and scientists in a light that is not the way it really works. We know that cookbook laboratory experiences are ubiquitous in school. And I'm not arguing that we shouldn't and don't have to give direction to students. But if you think about the way we have kids follow directions in the lab, and the way we have them write up lab reports, it all really comes together to portray to science that scientists follow a linear step-by-step method when that's not the case. How we speak about science. I think about, we shortchange things when we say things like, what does the data tell you? And of course, data doesn't tell scientists things. Scientists have to interpret data. When we talk about words like theories and laws, there's all sorts of ways that teachers and other sources, the way we communicate about science misportrays the nature of science. And then there's these intuitive notions about how knowledge is developed and accepted. To some extent, nature of science misconceptions make sense. I'll give you an example. Most people think that if you want to know how nature works, you go out and look at nature. Well, sometimes yes, but oftentimes no. Oftentimes you have to ignore what you see in nature to understand the natural world. My favorite example is the law of pendulum motion. If you want to know how pendulum work, and if you're a physics teacher or a physical science teacher and you teach about the law of pendulum motion, you might be surprised that that was developed by ignoring how pendulums swing and by using mathematics. And as Galileo was wont to point out, you'll never figure out pendulum motion by watching pendulum swing. So we have rationales for learning about the nature of science and for teaching about it. I want to emphasize that we don't teach the nature of science just to help kids understand the nature of science. Teachers who understand the nature of science are in a far better position to understand students' difficulties learning science ideas and the tenacity of their misconceptions. There's been a number of books written about how science ideas, if you look at it from a straightforward view of the natural world, they don't make sense. All you have to do is go out and look at nature and see it doesn't seem to make sense. And you look at how science themselves had to abandon oftentimes everyday thinking to understand the natural world. And so when you understand the nature of science as a teacher, you can see why students have trouble understanding and deeply accepting many of our science ideas. I don't want to say all the science ideas, but many science ideas are counterintuitive unless you understand the nature of science. It assists teachers in understanding why telling and showing do not compel students to change their thinking. It's not that telling and showing aren't part of science, but it's not going to be sufficient. And we have research that points out that students who understand the nature of science, they understand the complexity of scientist struggles. And so knowing that scientists struggle to piece this all together, the students themselves are more likely to persevere because they know this is not straightforward. I love the history of science to illustrate much about the nature of science, because you see scientists, and with our common knowledge today, we think, well, it's straightforward. DNA is, of course, a double helix. But if you read Watson's double helix books, they don't know what the answer is, of course, so they're trying to figure it out. And they're really having a hard time doing this. And so again, I want to emphasize that we can really use the nature of science to leverage when our students struggle to help them understand that scientists struggled. We know that when the nature of science is taught well, that it can improve students' attitudes toward an interest in science and science education. Many students find they don't want to major in science because it doesn't look like it's creative. There's a lot of things they don't, understand how science really works. If they did understand that, they'd be more interested perhaps in science careers and also in science education. We know that understanding the nature of science plays a significant role, not the only role, but a significant role in socio-scientific decision-making. Mitchell's written a book called Unsimple Truths and talks about how policymakers and citizens oftentimes use naive views about the nature of science, and therefore they make poor decisions regarding socio-scientific decisions. A recent article came out about how the public and policymakers wrongly think we have to wait for certainty in science before we can act. And that's disastrous. If you're looking at certainty as an absolute truth, by the time that comes about, it's well past when we had to make the decisions. And so that plays out in COVID-19, it plays out in climate change. If we had made decisions on climate change 30 years ago when it was becoming pretty clear, but people kept pointing out that it wasn't certain. And here we are 30 years later in a much, much poorer position. And again, we know that it's important for truly understanding important science ideas. If we want the kids just to memorize stuff, then the NOS doesn't play such a huge role, but we really want them to understand it, because I'll come back to pendulum motion. Why is pendulum motion dependent upon conditions that can't exist? You have to have a point mass. You can't have a string. You can't have friction. And Galileo's contemporaries even said, what are you doing, Galileo? Because in the real world, there aren't point masses. You need a string for a pendulum, and there is friction. But if you work with what Galileo put forward, and this is what we teach kids, that a pendulum depends only on the length of the string and gravity, that depends on those impossible but idealized conditions. But then you ask the question, why do we use that idea? And I don't have time to go into that right now, but you can get kids to buy in real quickly why that's needed, and they more deeply understand pendulum motion. The same is true with biological evolution and many other science ideas. If we really want kids to deeply understand the science content, the nature of science plays a key role. So what do we do from research? And this is going to be very important, I think, in your work with your workshop. We know that implicit instruction that faithfully reflects how science works does not change students' NOS understanding. And this means that, for example, even research has been done where you put teachers and students in laboratories to work with scientists. That does not tend to change their understanding of the nature of science. Now, that's not surprising because it's all implicit. It doesn't mean that those experiences aren't important, and the experiences that you're going to have with scientists are very important. But the key is, if we want to change nature of science understanding, we have to overtly draw their attention. So in cases where teachers and students have been put in labs where overt nature of science instruction occurred alongside those experiences, it has been shown to assist in understanding the nature of science. And that's what the second point is. Learners' attention must be directed to NOS ideas in a way that mentally engages them in thinking about those ideas. We know that multiple context with extensive scaffolding is important. Now, I'll illustrate that in the next slide. But we do know that teacher implementation of accurate and effective nature of science instruction has been problematic. And it's been problematic because teachers have so much on their plates. They seem to be being asked to do just another thing now. It's problematic because many teachers have not read much about the NOS. They've not taken a NOS course. So on this next slide, I want to talk about how the nature of science can be part of everyday science instruction. I'm going to break this into three broad categories. Many of you may have done black box activities. These are ubiquitous. Students have to try to figure out how something works that they can't see or what something's like on the inside. Those experiences are valuable for introducing the nature of science ideas, but of course, it takes time away from instruction regarding science content. And so you can only do so much with black box activities. We also know that black box activities really don't change students' NOS ideas because, as students are apt to point out, scientists aren't working on black boxes, they're working with the natural world. And so now when we get to everyday science instruction, you can think about the activities you have students do from elementary through university, where you have students have to make more decisions, because a student who's actually collecting data and has to make sense of it comes face to face with the data doesn't tell them what to think. They've got to make sense of the data. They come face to face that they're not following some step-by-step method. It's an iterative process that has many different approaches. These experiences are important, and notice that these take place in the context of teaching science content. So they're seamless with teaching the science content if a teacher overtly draws students' attention to NOS issues in these experiences. But in research I've done it, and it's becoming better established because I put forward a concept paper, this is not sufficient because students can always say, yes, we're struggling with these things, but scientists are smarter than us. Scientists have better lab equipment. Scientists have equipment that actually shows us pictures of the atoms, which is not quite the case. And so we need to bring in the work of and words of scientists. And I know working with scientists in your project, this is something I hope you'll do is pay attention to how the scientists work and pay attention to their words. It really assists students in understanding the nature of science when scientists speak accurately about the nature of science. Einstein was fond of saying that scientists don't have a scientific method. Peter Medawar, Nobel laureate, he wrote a piece called "Is the Scientific Paper a Fraud?" And he wasn't talking about do scientists cheat. He was saying that if you look at the way the papers are written in articles, they misrepresent how science really works. Because of course the article is giving you a straightforward view of all the information, whereas in the real work of scientists, it's not that straightforward. And so bringing in the work and words of scientists can assist students in understanding the nature of science. And the scaffolding back and forth between these different things is crucial. What I mean by that is if you're bringing in the work and words of scientists, you can say to students, how was that like your work when you did the black box activity, whatever that might be? How was that like the work that you did in the lab or in activity that you did in class? and you go back and forth along that from black box activities to the work and words of scientists. You can scaffold to the laboratory activities. Any one of these directions you can and should do. I realize this is very little time, and I want to make sure you have additional resources. And so I've given many resources for distribution. For those of you teaching elementary, I want you to know this is just as relevant for that. Particularly, misconceptions can be promoted by putting up posters in rooms that the scientific method, and so in elementary school I always tell people it's important not to convey misconceptions, and that's true of the high school teachers as well, because there's posters at the high school level that talk about the scientific method. We've been fighting that for 50 years now. We're making progress, but it's just something we really seemingly can't get rid of. But elementary teachers also are in a great position to have kids do activities and draw their students' attention to the many methods that the kids can use. Draw their students' attention to how they're collaborating together. Draw their students' attention to how people of all cultures do science. And then you bring in the work and words of scientists to bolster that. And so I taught high school, so I draw so often from my own examples teaching kids, but I don't want you to think it's just something done at the high school or middle school level. It's really something that starts at elementary and should go all the way to the university. And I'll leave you with this. I work with university faculty in science to assist in teaching the nature of science. I was part of a very large Howard Hughes Medical Institute grant that we were working to actually get more authentic laboratory experiences in undergraduate science courses. And to show you, and this is just anecdotal, but to show you how the misconceptions run all the way up to the university, we're trying to get students to do real research. And so they're assisting faculty and researchers, undergraduates. And one student commented, I didn't see the purpose of all this. What are we doing this for if they don't really already know the answer? And it's like, well, that's why they call it research. But anyway, I thank you for your time. And I wish I had more time with you, but I think I did exactly 20 minutes.
That was great. Dr. Clough, thank you so much.